Welcome to the last talk in what, in my opinion, has been a pretty amazing conference. Before I begin, I'd like to thank everyone who organized this conference and all the speakers. It was really hard. Almost every single session, I had to flip a coin to decide. And now I got a lot of things I got to go watch because I missed them. So thanks for that. Thanks for giving me a lot of extra work. So I'm here to talk about Halo. And to kick things off, I'm going to introduce myself and then hopefully energize the audience with a 40-second video. So my name is Somuah. I work at Microsoft. I specifically work in a group at Microsoft called 343 Industries. 343 Industries is a game studio within Microsoft that owns everything Halo. Now, up here on the slide, you'll see a list of things, and these are just things that we've either released or announced in the past 3 years. Halo's been around since 2001. It was previously owned by Bungie. It's now owned by, and the legacy's continued by 343 Industries. So to kick things off, I thought I'd show you guys a portion of a video that we made when we started working on Halo 4, the backend services for it.
Halo is a rich, immersive story with millions of loyal and dedicated fans. We deliver an exciting and engaging experience to these fans. They need to know what the hot playlist is today. They need to know what the challenges are. They need to know where their friends have been, what their friends have been playing. Have their friends gotten more medals than them? They need to know all of this, and they need to react to it and interact with their friends in real time. We need to deliver hundreds of thousands of updates per second to millions of players across the Halo universe. We need to get them the right information to the right device at the right time. There was nothing off the shelf that solved the problems we needed to solve at the scale we needed to solve them. So we turned to Microsoft's Extreme Computing Group.
Hundreds of thousands of requests per second across thousands of servers in real time. These guys are crazy. But in extreme computing, those are the kind of challenges we'd like to tackle.
So that's a little video that gives you an idea of the way we were thinking about Halo 4. And I'm going to walk you into a little bit more detail in a second here. So mostly what I'm going to talk about today is how we used technology from Microsoft Research that is now publicly available called Project Orleans. And the way I like to think about it is it's a programming model and a runtime for building cloud-native services. Now, I didn't make up that term, cloud-native. I think the first time I heard it was from Adrian Cockcroft at Netflix. And the way I think about cloud-native services is when you move your application to the cloud or when you're writing a cloud application, you lose some of the things that you had when you were doing your own on-premise stuff. Like, as an example, you don't get to schedule maintenances of the hardware anymore. It just happens, and your code might need to be moved to another machine, which means your VM's going to get shut down. And that tends to not work out so great for code that's expecting to be on the same machine for a very long time. If, for example, you're expecting your hard drives to be around for a very long time, that's generally not the case if you're writing to the actual physical hard drive in a virtual machine cluster. And so when we early on decided we wanted to build Halo 4 services in Windows Azure, we decided that we wanted these services to be cloud native. We wanted to build services that were actually built with the cloud in mind. And I'm going to walk through how we got there. But before I do that, I want to give you a little bit more context about some of the data problems that we had and the real-time problems we had. So one property that Halo owns is called Halo Waypoint. And this is a series of apps for various mobile devices, as well as a website that people can go to and learn about what they're doing or what they've done in the Halo universe. They can also go and check in on their friends. I do that a lot. You can go and look at your service record, and it'll show you things like your competitive skill ranking. It'll show you what your service ranking is and what classification you have if you've reached that stage in Halo. You can dig even deeper and see past games that you've played and how you did on each game. If it was a multiplayer game, you can see how your team did. You can go even deeper, and I like to do this with my friends, and look at how far they've made progress on various things like the campaign or Spartan Ops, which is a player versus the environment multiplayer thing. If you're playing war games, which is our matchmaking thing, you can dig very deep and get really detailed statistics about things like how many times have I used this weapon, how good am I at this weapon. And I like to do this against my opponents. So for example, up here on screen, I think we have Bravo up here. And you'll see that if you look at his skill with the battle rifle, it's very clear that if you see him holding that weapon, you should turn the other way and run as fast as you can. And that's exactly what I do, because he's really good with it. You can also do things like learn about how good you are with weapons, which weapons you suck at, so just stop picking them up. So this is the kind of detail that we make available to people with Halo. And as you can see, if you think about having this type of information for every game of Halo that people have ever played, we have a huge data problem. But as I mentioned in the video, a lot of the data that we need to get around to our users also needs to move around in near real time. Because, for example, if how many people here have played Halo 4? Oh, pretty decent number of people. One of the features in Halo 4 was join in progress. So if you went online and your friends were in a game and that game wasn't already at capacity, you could jump in and join them in the game they were playing. In order to do this, you needed to know that your friends were playing this game and that you could jump in, and you needed to take action before someone else took that open slot in the game. And so that's the kind of thing where if you get that information 10 seconds after that actually happened, it might not be useful. It might not be actionable information. So that's one of the cases where you need something to be a little bit more real time. So when I joined the Halo team, I've been there for about 3.5 years. I joined back in January of 2010. One of the interesting things to me was I was a huge fan of Halo, and 343 Industries had just picked up the Halo mantle and started to work on Halo 4. And there was something poetic about that for me, because one of the things that they were doing in the actual fiction was, if you've played Halo 3, the hero, Master Chief, goes to sleep. And then in the next thing in the series, in Halo 4, he gets woken up. That's the first thing that happens in the game. I'm just clicking through some more slides of the different things that you see on Waypoint. But, wait, oh, I'm going the wrong direction. Hang on one second. So waking up the Chief was both for us, 343, Halo 3 came out in, I think, 2007. So in 2010, we were like gearing up, or they had already been working on it, but I joined to work on the next iteration, and we were literally waking up Master Chief. And that meant building a bunch of services that were going to run in the background when people were playing Halo 4 or when people visited sites like Halo Waypoint. Services like presence and matchmaking. Some of these services are provided by Xbox Live. Some of them we had to augment. We have a cheat detection system that tries to make sure that everyone's playing on a level playing field. We keep track of game history, as you've seen. And then people have this whole career thing where they go through their progress and they unlock things that they can do, unlock armor and stuff like that. And we need to build the services that manage all of this. Another really big thing in Halo is the user-generated content. You can customize maps. After a game, you can go back and take pictures of certain places in the game as you're playing it. So if you've got a really good kill shot or a really great grenade throw, you can go take a snapshot of that, upload it, and so you can make fun of your friend forever. I'm not that good, so I don't get to do that often, but I look forward to being able to do that more. So as we're working on these things, as we're starting, like, we look at this list of services we have to build, and like, how are we going to build all of this? It's pretty clear to us that we want to go to the cloud, and we'll talk about the reasons for that in a second. But we have a lot of services that we need to build, and we're staffing up our team as we go. Some of the challenges that we have when we're building our services is, like I said, near real-time responsiveness of the service. We want cost-effective scalability. It doesn't matter if you've built a service that can scale in the cloud if it's too expensive as you scale your service out, if you can't afford it. The social graphs in Xbox Live and in most games are constantly evolving. People are unfriending people are making new friends are coming online and going offline. And so both the static graph of who your friends are as well as what your friends are doing, that's constantly changing, and we need to keep up with that. You need global high availability. I'll talk about that again in a second. Strong uptime requirements. Your service doesn't get to go down, at least in the initial days. And at peak times, rapid incident response. If something does go wrong, you need to be able to fix fast, fix on fail, and get the patches out there. And the storage scale, as you can imagine, is pretty huge. And then, like I said in the video, the requests per second can be pretty huge depending on the nature of the service. So this is a hypothetical, fictitious load graph, but it's meant to give you an idea of what happens on a big game launch. Usually you'll have a little spike as people in various parts of the world start coming online. But for a game like Halo, like once it starts hitting the East Coast, the US, like traffic just spikes up because tons of people are standing at midnight. They're all in line at some store. They get their copy of Halo. They go home. They throw it into their console, and they all come online at the same time. I wish we could give people like times, like you don't come online until 3 a.m. But we don't get to do that. So people come online as soon as they get the game. And I think this is actually going to increase. You're going to see more of this as we start having digital distribution of games, or more digital distribution. As soon as people get the game at midnight, you're going to see you don't get the little delay of people having to drive home anymore. It was kind of nice. Now you don't have even that. And so you're going to see more people come online almost instantaneously. And I've been working in services in various capacities for 11 years now, and I have yet to meet someone who is as intolerant of downtime as an avid video gamer. On launch day, your game doesn't get to go down, and if you look at the comments that people post when there's downtime, it's kind of scary, and for good reason. They paid a lot of money, they were waiting for this day, and it's super anticlimactic if the game is not available. So that's something we really need to work very hard to avoid. Over time, your load steadies out, and this is one of the reasons we like the idea of cloud computing. I can get a bunch of VMs, put my service on them, and then over time, as my load steadies and I have an idea of what my steady state looks like, I can adjust the number of servers that I have in production. And that's something that I couldn't do if I went and just wrote a big check to either Dell or HP or whoever I'm getting my servers from. Because, I've never tried it, but I imagine if I called Dell up and said, I need 100 more servers within the next hour, they're probably going to tell me, you're out of luck, buddy. But when you have cloud computing, you can just go click something there, and over a certain amount of time, you're going to get some more VMs. And that's very nice for us. So we decided we were going to go use cloud computing, and we decided to use Windows Azure because looking at it, there are a bunch of advantages. In particular, the feature of Windows Azure that we used is the Windows Azure Cloud Service, which a lot of people describe as platform as a service. So unlike something like EC2 where you go and you get a whole VM, the way Azure's PaaS system, or what they call worker roles, works is you just give them an executable and say, please execute this on this number of machines. You don't install an operating system. You're not responsible for patching the operating system. Azure handles all of that for you. They just spin up the machine, deploy your executable, and launch it. And you can have them launch more than one or do some startup stuff. But it's a little bit more convenient than having to manage an entire virtual machine. And I hate having to manage operating system upgrades, so I was like, yes, let's do that, because I can be more lazy. So this is a high-level overview of, extremely simplified overview of what the cloud stack for Halo looks like. We have a bunch of varying devices on the front end, and they all talk through a front door, which, if you're familiar with Nginx, we have something similar that we built, a very lightweight HTTP front door that forwards everything to a middle tier, a middle cluster of machines that do all the processing. And we have lots of services. That previous diagram I showed, where we showed all of those different services, almost all of them look very similar to this. And then on the back end, we do a bunch of stuff with HD Insight, which is Microsoft Azure's iteration of Hadoop. And we put all of our stuff in Azure storage. The way we came up with this model is, how many people here have heard of the warehouse computing abstraction model, or data center computing? So basically, there's this model where you think of your entire data center or your entire software cluster as though it's one computer. And that's kind of the way we thought about this as we came up with this model for our services. And it's kind of great. You treat it as though you've got this giant, massive multi-proc machine, and your front doors are just this massive scaling out network interface, and then you treat your backend storage as though it's one big persistent hard drive. That's great, except for a problem. Concurrency is still hard. Distribution, high throughput, low latency, all these things make it even harder. And even on one box with multiple processors, I find it a little bit hard to do things when I have to do locks and semaphores and all these things. It's like, it's already hard, and now you're telling me I have to scale it out to multiple machines, and I have to still deal with this challenge? That's kind of annoying. So the first thing we tried to do was figure out how we wouldn't make this the problem that we were always fighting with when we were building our services. And so we turned to the actor model. Show of hands, how many people are super familiar with the actor model? How many people have heard of it but don't really get it? Great. I'm not going to focus on the definition of the actor model, because what I've discovered is that trying to describe it and get into it leads to some very heated, very opinionated debates, and that's not what this talk is about. But I will say that that's where we started. And when we first thought about it, we were like, oh, well, there's this Erlang thing that works really well. They've got the actor model there. A lot of other things like Scala has a nice actor model in it too. But a lot of our developers already knew how to do stuff in .NET, and we wanted to stick with .NET. We also wanted to try and figure out how to make things work on the Microsoft platform, being part of Microsoft. So we said, let's think about how we do that in the Microsoft world. And as we thought about it, purely serendipitously, we discovered Project Orleans. So Project Orleans is a distributed actor runtime designed for the .NET framework because they're a Microsoft research team. But again, I'm going to avoid talking too much about the actor model, and fortunately for me, the Orleans team has a different term that they use that I'm going to use called grains. So the core thing, the atom of computation in the Orleans system is this thing that they call a grain. And you write a bunch of grains, and these grains all execute in a process container called a silo. And then within your data center, you can have lots of different silos, and they'll all communicate with one another, and Orleans does a bunch of magic that I'm going to talk about behind the scenes for you. This is all really beautiful. But what's a grain? Let's talk about that for a second. So if you use Halo as an example, one example of a grain that we have in Halo is the game grain type. This is a grain that represents every single game of Halo that is ever played. We create a grain for that. And so first you write a .NET class to define your game grain as a type, and then at runtime, as things are happening and as data is coming in, you'll create an instance of that game grain for a single game that gets played. Now, there's no actual manifestation anywhere of an instance of a grain. What you actually have a manifestation of is an activation, and I'll talk about the difference between those two in a second. But this is a really interesting concept that the Orleans team brought in, a difference between the actual instance that you're talking to and the activation, which is a manifestation of that in memory somewhere. So the cloud native runtime of Orleans works kind of like this. You basically have a bunch of machines sitting around your data center, and as things are happening, as communication is happening, data is coming in, you're making calls to write to databases and stuff, the Orleans system is automatically activating these grains in memory on appropriate machines for you. So what happens in the cloud native environment when you lose a machine or when you run out of space on machines and there's no space? Well, you can have your system auto-scale, and a lot of cloud providers provide this auto-scale option for you, and you'll get another machine. The Orleans system takes advantage of this, and when a new silo comes into being because it's spun up a new machine, it'll start putting activations on that silo because that's the least loaded machine. Similarly, at some point, you might lose a machine, just boom, explosion in the data center, and you lost a rack. When that machine becomes unavailable, all the other silos are gossiping amongst one another about the availability of the silos in your cluster. So when they all detect that that guy's unavailable, Orleans will create new activations of the grains that existed on that previous silo that became unavailable. It'll just create them on another silo. And I'll talk about why this isn't a pain for you as a developer when we get to code. And then when that machine becomes available, it'll also be very lightly loaded because we're assuming it rebooted, and then it'll get some new activations on it. An aside here, let's assume that it didn't actually reboot and it just became unavailable due to a network partition. As soon as it becomes voted as unavailable, when it comes back, it'll detect that, and it will immediately just restart itself anyways, because for all intents and purposes, it was dead. So let's dig into grains for a second here. Grains, one of the ways the Orleans team describes these is virtual actors. And the reason for this virtual word there is the grains instances always exist. There is no notion of creating a grain or creating a manifestation of a grain. You just talk to the grain. So there's a game out there, a game starting to get played, you just start talking and sending messages to that grain. You don't create it, and it never fails. You just start calling methods on it. On demand, the Orleans system in the background will create these activations for the grains as they're needed. If you send a message to a grain that doesn't have a current activation, Orleans will create it in the background for you and start sending messages to it. And then if it dies, the next time someone sends a message to it, it will again, Orleans will again create it and start sending messages to it. So as a result of this, if your servers are dying in the data center, you don't really have to worry about it unless they're dying all the time. If you just have a single outage in your data center, one machine dies or a machine gets migrated, a VM sometimes gets migrated from one physical machine to another, that's not something you spend any time worrying about. You just let it happen, and your code should recover from that gracefully. There's one case where you can have stateless grains that you don't care about the state, and for performance, Orleans can actually create multiple activations of that grain across your data center to allow you to scale better. The location transparency is possibly my favorite feature of this, because when I think about it, when I'm developing apps on my local machine, I never think about which memory stick my object is going to get allocated to when I'm creating an object in C# or Java. I'm never like, yeah, let's put that one on memory stick number 1, and then when I need to interact with an object, I don't ever address it by talking about the memory location or the memory stick it's in. I just talk to the object. And Orleans gives me this ability distributed across multiple machines, which is very useful. The other thing that Orleans has that you'll see in a second is that because of the location transparency, I can serialize and send references to grains. I can send them around. I can even persist them to cold storage. Someone can deserialize that reference to a grain and start sending messages to it. It might exist, it might not, but it's going to succeed, because if it doesn't exist, Orleans will activate it and start sending messages to it. That's a really interesting, useful concept there. And the virtual actor concept, Orleans is the only example that I know of it existing, but I think it's a really interesting concept, particularly in the world of cloud computing where things are failing all the time. So let's talk about the execution model for grains. Grains are all executed by default as single-threaded tasks. The advantage of this is, even though I might have millions of grains executing in my data center at the same time, I don't actually care about worrying about concurrency, which, as I said, was the original problem that I really wanted to get around. And so all messaging between grains all communication between grains is done using messaging. And within a grain, even if a grain receives multiple messages at the same time, it's all run and executed in a single-threaded manner. Now, if I have a hot grain, this is a problem, and so you can opt out of having a grain be single-threaded, but by default, that works pretty well. And most of the time, we don't have really hot grains. Like I mentioned, we have one grain for every game that's been played in Halo. We also have one grain for every player that's ever played Halo since we launched Halo 4. And because of the fact that Orleans does automatic activation of this, it's not a problem that there have been literally billions of games played. Who cares? Because Orleans will activate these game grains when they need to be activated. And then if they don't receive messages for a long period of time, it'll deactivate them, and then they can come back when someone needs them. And so there are literally billions of grains across our clusters, and we don't ever have to worry about their memory, how much memory they're using, unless for some reason we have an extremely high load of users. And the only thing we have to do in that case is just add more machines to it. So I kind of like this model of single-threadedness, and there's no shared state. Anyone familiar with the actor model gets that that's one of the things that you're supposed to have. And then you have this, Orleans enforces this notion of cooperative multitasking. Everything that you do in a grain, all the public interfaces of your grain, have to be asynchronous. And this means that a single grain isn't going to tie up an operating system thread. So a grain does not map directly to an operating system thread. Orleans has a scheduler that receives messages targeting a grain, and then it'll manage all the operating system threads it has and schedule tasks. And because the grains are designed, it enforces this asynchronous model. If a grain isn't actually receiving messages, it's not actually using up any CPU. And then over a longer period of time, Orleans will remove it from memory, and it's not using memory either. So let's go quickly into what it's like to develop grains. Now this code is mostly C# code, but if you're familiar with Java, it should be pretty easy to follow. So the obligatory hello world example, there's not really a whole lot going on here. The first thing you do is define an interface for your grain. And there's the iGrain marker interface that tells Orleans that this is a grain. And then you implement a bunch of methods. And then the task generic type there is the way you have a method that is asynchronous. So when you call it, instead of getting back your string, you're going to get a promise of a string that you can then run continuations against. And then the way you implement it is you implement that interface that you just defined. Grain base is this base class that you inherit from, and it gives you some stuff you can override. And essentially you write code that's going to return the result when you're good and ready. Again, this is an asynchronous method, so you could asynchronously call off to a database, get some stuff, do some other, make some other calls to other web services. If you do them all asynchronously, then you're not going to tie up any threads while all of this is happening. And then you can return by setting the results on your task. So the other side of it is, how do you talk to a grain? And so if I were writing this static method to talk to a grain, the first thing you'll notice is there's a hello factory. I had an iHello interface that I defined, and at compile time, there's tools that will essentially just look at your interface and generate a factory class for getting at a grain. And every grain in Orleans, when you define the grain, you define how it's identified. So instead of thinking about grains in terms of what machine they're on and like in some other object identifier, what you get in the Orleans world is whatever identifier makes sense for your grain. So if this were a game, I would have a game ID, and I'd use that to identify my grain. If it was a player, I'd use a player ID to identify the grain. It can be a string, a long, or a GUID. And then when I pass that to the hello factory, I get back a local interface reference to my grain. Now, that doesn't mean that the grain activation exists anywhere. I can do anything I want with that iHello instance there. When I actually make my call to the grain there, when I call say hello, that's when the Orleans runtime will be like, well, do we have a grain somewhere in the data center that has this identity? If it doesn't, it will look it up in the activation table. If it doesn't, then it's going to go and activate it on the most available machine in the cluster. And then so over there, you see that keyword await. I don't think Java has the equivalent of this. Essentially, that turns the remainder of this method into a continuation, and it registers it on the task. So you call await on a method you use the await keyword on a method that returns a task, and then everything after that becomes a continuation that gets executed when that method returns. So even though it looks like I might be blocking on the say hello call, this is actually not a blocking method. This method will then turn into a method where it'll call say hello, and then the method will return, and then the remainder of the method is going to execute when the grain returns its call to me. So let's quickly run through a more detailed example. This is actually very similar to the present system that runs in production for Halo. It's one of the first services that we wrote on the Orleans runtime. And if you download Orleans and you look at the samples, some of this code is there. So what does the present service look like? Like I said before, the present system is what tells you what your friends are doing, so you have near real-time processing needs. Most of your state is in memory, though, so that's something that you don't have to worry as much about state persistence, because every system that's playing in Halo is continuously pinging the service with its state. And so even if you lost the entire service, if every single machine rebooted, within a certain period of time, everybody's going to ping you with their state again, and you'll recover from your failure. So that makes it a less risky service to write. But we've written things where there are persistent state, and if you have questions about that, we can talk about that later. You generally have a fraction of your total user base online, but you need to maintain a graph of those online users to figure out what their friends are doing and stuff. And you want the low latency and a high throughput. Every Xbox that's online is pinging the service periodically to say, this is what I'm up to. So based on that, you have some inherent race conditions. But let's look at what this call flow looks like. So a game client, let's think hypothetically at Xbox, comes and pings the service with its state and says, this is user XYZ and I'm playing in game number 4. The first thing that we do is we have a grain that is a stateless grain, I mentioned that before, and all this presence grain is doing is receiving that heartbeat command from the HTTP server and doing a bunch of crunching on it. There's some decryption going on, some decompression, and extracting a heartbeat, taking that payload of heartbeats and turning that into a game status update. And then it figures out based on reading that, it figures out which actual game the player is in, and it forwards that heartbeat data and game status data onto the game grain for the game that player is currently playing in. Now, the game grain is going to take this, and it's got a game status update, so it's going to update any information it has about that, and then it's going to turn around and forward that information on to any players that are currently playing in the game, anything about that state. And in this example, there's only 2 things it tells players. If a new player is in the game, it says, hey, join the game. I'm just letting you know. And if a player has been removed from the game since the game grain last got an update, it'll tell that player's player grain, you are no longer in this game. And that allows the player grains to know which game the player is in. And this is all interesting because I can then connect with a mobile client to another front-end server, and I can go to my player grain and say, hey, what is this player doing? I could go to my player grain, or I could go to one of my friends' player grains and say, hey, what's the current deal? What's going on? What game are you in? That'll return the game grain to the front door, which can then turn around and talk to the game grain and get get what's going on in the game, get the actual game score, for example. The other thing that you can do here is Orleans supports this notion of subscribing for notifications. So then the mobile client, or rather the front door that's talking to the mobile client, assuming we've set up some sort of bidirectional WebSocket connection, it can then subscribe to receive updates to the game from the game grain. And then as new heartbeats come in, the game grain can push updates of status to the mobile device. Well, through the HTTP server, it'll push updates down to the mobile device. So this gives you a way for you to have really fast updates moving around the system. Now, if you picture this running in our data center, like I said, if you have 100,000 concurrent games running, you're going to have 100,000 of these game grains distributed across your data center. If you have 1 million players online at the same time, you're going to have 1 million of those player grains. But all of this all the communication and figuring out which machine to send messages to is being handled in the back by the Orleans runtime. So the next couple of slides have actual code for how this works, but I don't think I'm going to have enough time to go into too much detail about it. So I'm going to go rather fast through it. But if you go online, you can actually look at the code and dig into what it's doing. So again, we get a heartbeat from the game. And the way that looks is the heartbeat method basically decrypts the heartbeat. And then over there, you'll notice that it's getting the game grain, and it's calling update game status on the game grain. Fairly straightforward. It's basically decrypting the data and forwarding it along to the game grain. In the game grain, we basically keep a list of the players in the game, the current status of the game, what's the score, and then we have a method where people can come and subscribe to receive game updates, like I showed in the example where in the diagram where the mobile device was subscribing to receive updates. The more interesting part of this code is the game grain calls the various player grains and tells them to update their status. So the first bit of this method, when you call update grain status, is it's going to take the status update and it's going to iterate over all of the player grains, all of the players, the GUIDs that it gets for each player, and it's going to check whether the player is new. That player means that player joined because that player is not in the game grain's internal state for which players are in the game. It's going to call each of those player grains in succession, tell them to join the game. This is not the best way to do it because in this example, we're calling each player grain and then we're waiting to hear back from that player grain before we move on to notify the next player grain. So that gives you a little bit of a delay. But one of the things that's interesting here is this should freak you out. I mean, I know I'm moving really fast through this code, but right there, I have a grain that is running on my current machine. I'm the game grain. And I just called another grain, and I passed it to this pointer. I just passed it to this pointer. That's a pointer to my local memory. How is that going to work when I'm calling another grain that could be on a machine that's across the street? Well, what Orleans does is when Orleans receives this join game, because remember, you got access to this by calling a factory method to the player grain implementation. The actual local implementation of player grain knows that it's going to receive a grain reference there, and it will actually serialize the grain identity and send that across the wire. And then on the remote end, you receive the grain identity. This means that you don't have to worry about the fact that that's a pointer. But this also means that in the time that I call join game, if after I make that call, the game grain dies, that pointer or that reference is still useful on the remote machine, because if they make a call to the game grain, it'll just create a new activation. Now, in this particular case, that might not be interesting because the new activation doesn't have status, but over time, that new activation will get the status, and I'll be able to make use of that reference. And then in this particular case, we ignore exceptions, but one of the interesting things about Orleans is that it also propagates exceptions from machine to machine. So if I call a grain and then an exception gets thrown, I can handle that exception. Here, because I'm doing the await, that exception will be handled in a continuation. So this is another example. This is where we're calling each player grain to tell them to get out of the game because they're no longer I got an update that says this player is not in the game. And the interesting thing to see in this example is we create a list of the promises, then we iterate over all of the players and we call all of them, and we call the remove method on them. And then at the end, we wait on all of the promises that we receive. So this is a much more efficient way to fan out a call and wait for all of them to return to us before we continue. And the last thing that happens in this method is that all the people who have subscribed, we have this helper method that will then notify all of them of the game status update. So if you have a bunch of different mobile devices connected, they all get updated. So the player grain code is really quick, very simple. The only thing that the player grain is storing in this particular example, in our code we actually store more data about it. The only thing the player grain is storing is which game the player is in. So if the player is not in a game, that's going to be null. If you've actually received a join game call, then we'll have stored a reference to the game grain for that player. And again, if we get a leave game call, we set that back to null. This is useful in the case of the client observer. The mobile device via the HTTP front end calls and says, hey, I want to get the current game of the player. That's a simple get call where it calls and asks for what the current game is. But then it's going to turn around and say, now, based on the fact that this player is in a game, I want to subscribe to receive all updates to this game. So you can build a little mobile client that's continuously updating when the game score changes. And then your game grain is going to update that. So the way that looks is Orleans also defines an observer interface, which allows you to define an interface for a client that is not a grain, that is still going to participate in all this Orleans goodness of reference passing and stuff like that. And you basically implement that interface. In this case, all you're doing is updating when you receive an update to the game score. And in this example, all I'm doing is writing it out to the console. And this is an example of how that happens in how you actually subscribe. You'd call the player and get their current game. And if the game is not null, and that is, you have an await call there because, again, you're remotely calling from your HTTP front door to this remote player grain and getting their current game, and that could take a while. It might not even be active. But as soon as you get that, then you could create your game observer and create an object reference which says, this is a remote machine. I've already opened a connection to a cluster of Orleans machines. Now I want you to be able to send messages back to me, and here's the interface, the game observer, that I want you to send these messages to. Now, unlike the grains, if your game observer dies, there's no way for Orleans to reactivate it because it's not running within the Orleans silo system. This is a remote client that has gone and registered with Orleans. Because of the fact that Orleans cannot reactivate your observer if your client machine dies, all methods to a grain observer actually have no return value. They all have to be void because if it's dead, Orleans doesn't even know. Well, it'll know because the client connection is down, but they don't want you to have to write error handling code there, so it's all void. And if you want to actually know when clients are dead, then you need to come up with your own way of polling to detect that, or resubscribing. So I want to talk a little bit. I've gone through the code examples. We used Orleans in Halo for building the backend for the Halo video game. But Orleans was actually built for a lot of other scenarios, and we've talked with the Orleans team about a number of scenarios because we use it for a bunch of different services, like the present service. We used it as a mobile backend for some of the stuff that we've built. But if you think about what you can do with Orleans and the fact that you can build a system where you have a cluster of machines that can handle millions of grains all running, or up to billions if you don't need them all active, running in memory at the same time, you can do a lot of interesting things. There's been a lot of people who have done things with Orleans using the Internet of Things. There's actually a build talk on that. And one of the things we do with Orleans is we build like an intelligent cache. Near real-time analytics is one example of a place where Orleans could be very useful. You could basically have grains that are receiving calls when you pull methods off of, for example, a Kafka queue, and your grains are doing some processing, forwarding it to another grain, and then eventually pushing it into persistent storage. And another example is intelligent caching. When we use Orleans to do the statistics for Halo, we basically have one grain that is responsible for every portion of our backend data store that we're writing data to. Because of this, we don't have to worry about concurrency issues as people simply call the grain. The grain is single-threaded, so I don't have to worry about race conditions writing to storage. And then once I've read from storage, I have this in-memory grain that can act as an intelligent cache for all of the data. So to summarize our experience with Orleans, we went from having these servers that we called a cluster to this system now that has a bunch of grains, and we don't actually think about the individual servers anymore. We just have a collection of grains that are running there, and as developers, we focus on writing code for these individual grains. We don't think about server number 1 versus server number 2, and we don't even think about how many servers. We have an idea of the order of magnitude, but that's pretty much all we worry about. And so we tend in Halo to focus on this. We've got our front doors, and we worry about what those look like, and then we've got our grains. And that's about it. So, am I going backwards again? No. So in summary, the benefits that we've gotten from Orleans in Halo, huge benefits in developer productivity, separation of concerns. Developers building grains think about the application level logic and focus on building applications and building grains for Halo, not on the underlying infrastructure. I have this dream that someday developers are going to be like, what's a server? I know about grains and I know about front door. I don't know what this server thing you're talking about is. I know about the service. Is that what a server is? And then there'll be a couple of people who will still worry about the underlying infrastructure, but not as many developers. And in our world, that's kind of the case today. One of the other benefits we get is this nice, smooth scalability by default. This is actual test lab numbers that we worked with when we were working with prototyping this with the Orleans team. You see this nice linear graph as we added more servers. This was actually on-premise, not in the cloud, but as we added more servers to the cluster, you see this very almost linear scaling of stuff that made us feel like we were going to be pretty good when we got to the scale that we needed to be able to deliver. And that's a huge benefit when we think about being able to scale to the kinds of loads that we need in the Halo world. So that's it, and I am out of time. But the last things I'll leave you with is Orleans is available in preview, so you can go grab it and play with it. There's also samples available on Codeplex. And if you haven't and you play Halo, you should definitely check out Halo Waypoint. And that's it.